In the example that we looked at in the previous section, we saw that we could convert a difference equation or a transfer function in discrete time into a state space form pretty readily. And now we're going to look at the opposite transformation, the opposite translation, and see that it's also quite straightforward. We're going to start with state equations like are listed here and try to find a way to convert them back to a transfer function, which we could then convert back into a difference equation. In order to find a transfer function, we take the z transform of both sides of this equation. Here I have x of k plus 1, and by our z transform theorems, we know that's equal to z times x of z minus z times x of 0 being the time domain initial value of this state. And then we take the transform of that, and I simply get a times x of z plus b times u of z. On the opposite equation, y of z, c times x of z, and d times u of z. So the only place where there's dynamics are on the left-hand side, and that gives us this result by one of the z-transform theorems of a time advance. To rearrange this, we'd like to start with the first equation, solve for x, and then plug that into the second equation to eliminate x, and have an input-output relationship that relates u to y directly. So in the first equation, I am going to bring all of the x variables to one side, and I would have z times x of z equals, minus a times x of z equals b times u of z plus z times x 0. So the x of z stuff I'm bringing over to one side. We have to be a little careful proceeding. It looks like, oh, that's just z minus a times x of z. We have to be careful because this is a matrix and that's a scalar, and I can't actually subtract two different things of two different sizes. So we need to introduce in here the identity matrix, which doesn't change the computation at all. But then I have z times I times x of z minus a times x of z equals the right-hand side. And this is a matrix the same size as that, and those I can subtract. So zi minus a then times x of z equals the right-hand side. That is how we got this here. Once we have that, I can solve for x of z by multiplying both sides by the inverse of this. So zi minus a inverse shows up in two places on the right-hand side. And this x of z gets substituted over there for that x of z. And we get y of z equals something, c times zi minus a inverse b plus d times u of z, plus something else, c times zi minus a inverse times z times x of 0. The response of this linear time invariant system is represented in two parts. The first part we've shown it depends on the input to the system, that's the forced output. And the second part depends on whatever the initial conditions were in that system, and that's the homogeneous output. When we're looking at transfer functions, we always assume the initial conditions are 0. That's just a definition of a transfer function, so that goes away in that case. And I have that y of z is some function of z times u of z, so I can just call that g of z. And we say, oh, that must be the transfer function of the system. Y equals g times u. Whatever g is, it doesn't look like any transfer function we may have seen before, but in fact that is the transfer function to the system. So g of z equals y over u of z equals c times zi minus a inverse b plus d. If you're more familiar seeing transfer functions written as a numerator polynomial in z divided by some denominator polynomial in z, we can actually manipulate this expression to look more like what you're familiar with, and we can gain some insight when we do that. First, we need to recognize that the inverse of a matrix can be written as the adjoint of that matrix divided by the determinant of that matrix. The adjoint is a matrix, the determinant is a scalar. In this case, it's a scalar function of z. So I have a matrix function of z divided by a scalar function of z. When we make that substitution, we can write g of z is c times adjoint zi minus a times b plus, and that's all divided by that determinant. In order to get a common denominator, I also had to multiply the D matrix by a determinant zi minus a. Does this look like a transfer function? Well, in fact, it is. This here is a matrix operation. So we said C was a matrix that had a certain number of rows equal to the number of outputs, and it had a number of columns which were n. N was the size of the state. That adjoint is n by n, and the B matrix is n by number of inputs. And I forget what we called those. I think those were m, but I might have mixed up m and p. But when I combine all of this together, multiply it all out, I get a matrix which has a number of rows equal to the number of outputs and a number of columns equal to the number of inputs, which is exactly what we would expect for a multi-input, multi-output transfer function with a certain number of outputs and inputs. And you can do the same operation on D and see that as well. If I have a single output and a single input, this here condenses. The c times adjoint zi minus a b condenses to a 1-by-1 scalar function of z, and so does the d term, so that the numerator is in fact a scalar polynomial in z, and the denominator also is. This determinant also is. In any case, one very important observation for understanding state space forms is to recognize, by comparing the transfer function to the state space form using this process, looking at the denominator of the transfer function we get, the poles of the system would be the locations where determinant zi minus a equals 0, and those are, by definition, the eigenvalues of the A matrix. So if you have a state space form, you want to know what the poles are, you look at the A matrix only, and you find its eigenvalues. Those are the poles. Why is that important? The poles of a system tell you if it's stable or unstable, if it's fast or slow, if it oscillates, if it doesn't oscillate. It tells you all kinds of things about the system just by looking at where those poles are. We also need to look at one more concept with state space systems. And that concept is transformation. I already claimed that state space representations of any particular system's dynamics are not unique. The selection of the state is not completely arbitrary, but it's at least somewhat arbitrary. There's a lot of design choices that we could make. Some of them may end up with models that have better properties than others, in fact. But mathematically, they're all identical, input to output. Let's look at our standard state space form. This is something that should be becoming very recognizable to you. You look at that and say, oh, that's just a state space form. You'll see lots of them as we proceed. Here we are going to say that the state of the system X is equal to some matrix T times W. And the only stipulation on T is that it is an invertible matrix, which we also call a similarity matrix. So it transforms the X representation into a W representation, or vice versa. Let's see what happens if we follow through with this substitution. So if xk equals twk, then xk plus 1 is t times wk plus 1. And a times xk becomes a times t times wk, and b doesn't have an x, it remains the same. Y remains the same, but cx becomes c times t times w, and du stays as it is. I am going to multiply the state equation on both sides by t inverse to isolate w on the left side. We said that we required that t be invertible, so we can do this. So multiplying on the left by t inverse makes that identity. Multiplying on the left by t inverse makes that t inverse at. Multiplying by t inverse makes this t inverse b. What we end up with here is something that, if we look at the form of the equation, that is a matrix, that is a matrix, that is a matrix, and that is a matrix. I have something wk plus 1 equals matrix times w plus matrix times input. That looks like a state equation, except that instead of using the variable x for our state, we are now using a variable w for a state. But the form is the same, and the form is what matters. Same with the output, y equals some matrix w plus some matrix u. And again, this has the form of the state space model. And condensing these matrices down, so the t inverse at I will call a bar, and t inverse b is b bar, and ct is c bar, and d, just we call it d bar even though it's the same thing. I end up with a state space form in the state W instead of the state X that, it behaves in the same way as the previous state space form did. There are some things that are the same about this W form as the X form, and there are some things that are different. What is the same is the input to output mapping. So from U to Y, everything is exactly the same. I've changed an internal variable in my calculation, but that internal variable is completely processed by the time it gets to the output, and so the internal variable disappears when I'm done. So the conversion between U and Y for the W system and the X system, exactly the same. However, the relationship between U and W is different from the relationship between U and X, because the states are actually defined differently. So this is why I stated earlier that there may be some implementations that are better computationally or for some other reason, because maybe the X state that I started out with was not as representative in some way of the physical dynamics of what's happening as a W state is, or vice versa. So I would make a transformation to convert my state variables into a more easily computable form, or a more physically real representative form, so that there was some meaning to it, or any number of things really. But I claim that the input to output mapping of both systems is the same, and one way of showing that is to show that the transfer functions of the two systems are the same. So H1 is the transfer function of the X system, and H2 is the transfer function of the W system. Let's show that those are the same. H1 of Z, we saw how to do this already. It's C times Zi minus A inverse B plus D. So it's using the original A, B, C, D matrices. That's the key point. We're going to do some math on this to show that we can manipulate this to use the A bar, B bar, C bar, D bar matrices instead, which would give us the H2 form. First step, I am going to multiply by identity matrix right there and by the identity matrix right there. Identity doesn't change anything, so I'm welcome to do that. And the form of identity that I choose to use is T times T inverse. Remember, we said T was required to have an inverse, so I can do this. So that's what we do there. The next thing that we do is we change how we bracket stuff. So we bracket stuff like this instead of how we had previously bracketed things. But then we have to be a little bit careful going to the next line. So what we have here, if you look at that carefully, we have T inverse times Zi minus A inverse times T. And I'm claiming that it's equal to this. So let's look at this. Remember, when you are taking the inverse of a product of square matrices, you can write that as the product of inverses where I take things in the opposite order. So I have to take that one first and write its inverse, which would be T inverse. Then I take this, which I write as Zi minus A inverse. And finally, I take T inverse, which I write as T inverse inverse, or T. All of that, which is in fact what we had here to begin with. In the next line, we take the CT and recognize that we called that C bar. We look at this form here again in a different way. Now I multiply through on the left by T inverse and on the right by T, and I get Z times T inverse T minus T inverse AT, and that is identity, so that's just Zi minus T inverse AT. So everything, and all of that is inverted, of course. So all of that becomes this Zi minus A bar inverse because, T inverse AT is what we called A bar. And over here, T inverse B we called B bar. D we said was the same as D bar. So by rearranging, by manipulating using algebra only the H1 of Z, I get something which is exactly what we would have written down for our transfer function for H2 of Z using the A bar, B bar, C bar, D bar system of representation. So we conclude that the transfer function of our model is not changed by a similarity transformation. And since there are an infinite number of n by n invertible matrices T, there's actually an infinite number of state space representations that describe some system equally well. Maybe to convince or not, let's consider transforming this particular system, and you should recognize this system. It's the one we developed from a difference equation in the previous section of notes. So we have an A matrix as given, a B matrix, C matrix, D matrix as given, and this is the transformation matrix I choose. I could have chosen any invertible 3x3 matrix, but this one I chose because it's easy. And T inverse turn out to be the same thing, and multiplying by either one turns out to be really easy because if I multiply on the right by T, that flips the original entries left to right, and if I multiply on the left by T, it flips the original entries of what I'm multiplying top to bottom. So it's pretty easy to do this in a hand example. So in our transform system, we have A bar equals T inverse AT, T inverse AT, and if I multiply by this on the right, I'm going to flip left to right, so I'll have what? I'll have minus A3 minus A2 minus A1, 0, 0, 1, 0, 1, 0, and then multiplying that on the left, it flips top to bottom, and we get this result right there. B bar is T inverse B. I am multiplying on the left. That's a top to bottom flip. And we get this. C bar is CT. I'm multiplying on the right. So that's a left to right flip. And I get this. And D bar is unchanged. It was 0. It is still 0. So I now have a new A bar, B bar, C bar, D bar representation that I claim has the same input-output transfer function. So let's find that transfer function just to verify that that's the case. G of Z is C bar times Zi minus A inverse B bar plus D. C bar I simply wrote out. This is Z times identity matrix. A bar I simply wrote out. I haven't inverted yet, but I will. B bar I wrote out, and D bar I wrote out. Before I invert everything in the round parentheses in the middle, I combine together and get Z minus 0 is Z, 0 minus 1 is negative 1, 0 minus 0 is 0, and etc. for everything else in the matrix. To go from this line to this line, I had to invert a 3 by 3, and this is something that is a little unpleasant. We can do it by hand if you know how to find the adjoint and the determinant, or you can ask MATLAB to do it for you. You can even ask MATLAB to do it for you symbolically if you declare Z to be a symbolic variable and A1, A2, and A3 also to be symbolic variables. Alternately, you could look at the solution I give and verify that it's true by multiplying the assumed form of the matrix inverse, which is all of this, by the matrix to make sure you get the identity. In any case, I'm not going to do it right here, but you can do it and see that it is correct. To get from here to there, I chose to do this multiplication first because there's a structure. That multiplication says the product is 0 times first column, 0 times second column, 1 times third column. So the output is simply 1zz squared. That was a lot easier to do than multiplying with the b's first. And now I can multiply with the b's and see that the numerator is b3 plus b2z plus b1z squared. And I get, as a result, this transfer function. And that's exactly what we started with before we did any transformation at all. So we've now been introduced a little bit more formally into the state space form than we saw it in Chapter 2. Didn't really spend any time with it. Now we've spent a little bit more time with it. We've seen that we can convert between state space and transfer function and vice versa. We've seen there's transformations that we can do on the state space form. That's just about all that we need in this course of the formalities of the state space form. However, in the next section we look at a really critical application of the state space form that will be important to us later.